Welcome to episode 120 of Real Health Radio. You can find the links talked about as part of this episode at the show notes, which is www.7, so the word all spelled out, SEVEN health.com/120.
Welcome to Real Health Radio. Health advice that's more than just about how you look. And here's your host, Chris Sandel.
Hey everyone, welcome back to another episode of Real Health Radio. And this week it is a solo show where I'm taking a deep dive into a specific topic. And this week's chosen topic is the replication crisis. So this is actually an episode that has been a long time in the making, and I feel like I say that a lot these days with the solo episodes. They're coming out less frequently, with the last solo one coming out sometime in April, I think the beginning of April. And a big part of this is because I'm putting so much more time into these solo shows, and that's both during the gestation phase when I'm thinking about the topic, but also during the creation phase where I'm doing a lot more reading and researching before I metaphorically put pen to paper. So this week is a topic I first heard about nearly a year ago. It's something I've discovered has been talked about for more than a decade now, but it's become more widely discussed and more prominent in the last 4 or 5 years. So I am a little late to the party on this. And where I first heard about it was on the You Are Not So Smart podcast, which is a podcast that looks at human biases and fallacies. And there was an episode called The Replication Crisis. Now, given the fact that I often talk about fertility issues, you could be forgiven for thinking that the replication crisis is referring to issues with human reproduction. But this is not what this replication crisis is referring to. So the term was coined in the early 2010s, but actually goes back earlier than this. And it refers to the crisis within science in which scientists have found it incredibly difficult, if not impossible, to replicate results from a previous study. So a study is done and it shows a particular result. We then take that information as valid and it informs how we think about the world or human behavior or some specific functioning of cancer cells or whatever the study is about. But sometime later, whether that be a couple of years later or even decades later, when scientists try to recreate the original study to validate the results, they aren't able to. And science is talked about as something that is objective. It's meant to be the gold standard of working out what is true in the world, or more often ruling out all the things that aren't true, so we can arrive at a smaller collection of potentially right ideas that get more and more narrowed down. But while this is the impression, science is a lot messier than this. Science is done by humans, and us humans are fallible. We have mistakes or make mistakes. We have pressures placed on us. We have our biases. And all of this means that science isn't always as objective as we imagine that it will be. And my interest was then further piqued in this subject when I started to read about questions surrounding the work done by Brian Wansink. So Wansink runs the Cornell University Brand and Food Lab. He's done a ton of research on people's food eating behaviors and how they can be influenced by their environment. So things like how the size or the color of the plates or the type of music in a restaurant can affect how much people eat. And I was fascinated by his research. I've actually dedicated 2 podcasts to it. I did one looking at the research on children, and I did another looking at the research on adults. Unfortunately, I'm now not so sure how much of this is actually true, which is an annoyance for me after spending so much time putting together the episodes, but is a much bigger problem because the number of times that his work has been cited and used as the basis for programs and decisions by schools and bodies and governments, it's a problem. And this all began in 2016 when Wansink published a blog post in which he inadvertently admitted to encouraging his graduate students to engage in questionable research practices. And these are things I'm going to cover later on. And since 2016, scientists have been combing through his body of work and looking for errors or inconsistencies and red flags. And at this stage, 6 of his papers have been retracted and over a dozen have had corrections issued, with more, I imagine, to come. So after hearing the first podcast, I wanted to hear more. And then after hearing about Wansink, I really wanted to dig into this topic. And as I continued to think and explore the topic, I knew I wanted to dedicate an episode to it. So to get started with that, I did go to Wikipedia and did some reading on the replication crisis. And I know Wikipedia is hardly the gold standard, but actually it was incredibly helpful as a starting point. Because as I read through it, I went and found the majority of the articles that were linked to. I then read the original articles and the original studies, not just the abstracts, but the full articles. And if these then made reference to other articles that were of interest, I then made note of these articles and then checked them out. So in the end, I've gone through about 30 odd articles. That's the ones that I've found that were useful. And this probably totals a couple of days of doing nothing but just reading articles on the topic. And they touched on it from lots of different angles. And just so you know, all of the articles are then linked in the show notes so you can read them yourself if you wish. So there's a number of areas I want to cover as part of this episode. I want to cover what the replication crisis is, and I know I briefly touched on it already, but I'm going to go into a bit more detail. I'll cover why this problem is occurring. So there's been a lot written about this, so I'll go through what are the most important parts. I'm going to chat about what the implications are, because the results that fail to replicate cause many downstream issues, and so I want to highlight why this is such a problem. I'll then talk through some of the suggested solutions. So there've been many people speaking up about the issue and outlining ways that it could be avoided or minimized. So I'll go through what they think is best. And finally, I'll touch on an issue that might still persist, even if results can be replicated. And with all this, my goal is to make this accessible to a layperson. Even if you aren't a scientist or a researcher, I want you to find this interesting and informative. This is deeply important and a deeply important topic that affects everyone and is something that I also think is fascinating. So my hope is that I can convey this through the podcast. So the replication crisis. Let's take a step back from the actual crisis part of this and just focus on the first part. So the idea of replication. So replication has been referred to as the cornerstone of science. Science aims to reconstruct the unchanging rules by which our world and our universe operates. It's trying to determine that those same rules apply regardless of who is studying them. So if a finding can't be replicated, it suggests that our current understanding of the study system or our methods of testing are insufficient. Now, with science, the reality is that most studies aren't about creating overarching rules. It's about testing some small fragment of an idea. So when we take this set of people and put them in this specific context, this is what happens. Then you take a similar set of people and then you put them in a slightly different context and see what happens. And you do this more and more, and you start to see what findings can begin to be generalized across different groups or across different contexts. Or you look at some particular protein or some enzyme and how it reacts in one environment. Then you put it in a different environment, and you start to see what happens. And it's this jigsaw pattern where you have more and more individual pieces of information that then get metaphorically sewn together to create a bigger picture understanding. And obviously, I'm making some generalizations here because the field of science is incredibly broad, and so there are many different variations of this. But the idea is that we tend to use many studies looking at things from slightly different angles to try and understand the world. Now, with each piece of evidence, in theory, we should be double checking their results, getting a different group of people in a different lab to run the same experiment. If you then get the same or very similar results, our level of belief in that result would go up. If the same result is found 3 times or 4 times or 10 times in different studies, then we become even more certain. And I'm going to talk later about why this doesn't completely guarantee the results, but typically the more times a study can be replicated, the more confident we are in the results. And unfortunately, despite replication being the cornerstone for science, replication studies don't happen as much as they should, which is really a problem. So as I said at the beginning, the replication crisis has been bubbling for a while now. Certain areas of science have been affected differently, but one of the places that have been most hard hit is psychology. So to investigate psychology, the Reproducibility Project was set up. So this is a project that was led by the Center for Open Science and Brian Nosek, who started the project in November 2011. And Brian Nosek shouldn't be confused with Brian Wansink, who I mentioned at the start of the show. They are different people but have similar sounding surnames. So Nosek and his colleagues at the University of Virginia sought out to replicate 100 different studies. And these studies had all appeared in 3 prestigious journals. So Psychological Science, the Journal of Personality and Social Psychology, and the Journal of Experimental Psychology, Learning, Memory and Cognition. And each of the studies were published in 2008. And so in their initial publication, 97 out of the 100 studies claimed to have statistical significance. So meaning the results were unlikely to have occurred by chance and therefore have some underlying cause, which is potentially the cause that the paper was investigating. So as part of the reproducibility project, they went to great lengths to try and replicate the studies as closely as possible. So they contacted the original authors to find out about their methods, and they tried to best to do a like-for-like study. And the results of this collaboration were then published in August of 2015. And of the 97 studies that were originally statistically significant, this time around when they replicated them, only 35 of them, which is 36.1%, were statistically significant. And of the ones that were, the effect was much smaller the second time round. This means that just shy of 2/3 of the studies failed to replicate, which is a real issue. But it's not just happening in psychology, it's happening in many areas of science. Routine data audits conducted by the US Food and Drug Administration, so the FDA, between 1977 and 1990 found deficiencies and flaws in 10 to 20% of studies and led 2% of clinical investigators being judged as guilty of serious scientific misconduct. John Ioannidis from Stanford University has written many papers about the replication crisis and taking a critical look of how science is conducted. And the titles of some of his papers are rather telling. So one was called Why Most Clinical Research is Not Useful. Another is Why Most Published Research Findings Are False. He has a paper from 2010 called Contraindicated and Initially Stronger Effects in Highly Cited Clinical Research. And this paper was looking at medical science. And he looked at 49 clinical research studies in which 45 claimed that the intervention was effective. So the study looked at giving some drug or some vitamin, found that it was better than a placebo, and there was a statistically significant result. So these 49 clinical research studies were published in 3 major clinical journals, the New England Journal of Medicine, JAMA, and Lancet, or high impact factor specialty journals. They appeared between 1990 and 2003 and were cited more than 1,000 times. So not only did the vast majority of them show a positive impact of some intervention, these studies were then cited over and over again in other papers. So pointing to the fact that these studies were becoming assumed knowledge or a foundation of other research. Out of the 45 statistically significant studies, 7 or 16% were contraindicated by subsequent studies. Another 7, so again 16%, had found effects that were stronger than those subsequent studies, meaning that when a follow-up study was done, the significance of the results were weaker in the follow-up study. 20 studies, so 44%, were replicated, meaning that the other 25 or 56% hadn't had a replication attempted or published, with 11 studies remaining largely unchallenged. So like psychology, medicine is an area where there are replication issues, and it is something I'm going to touch on more as I go through this. So hopefully this gives you a bit of an understanding about the replication crisis and what it is. It is by no means restricted just to psychology and medicine, but affects science across the board. So why is this a problem occurring? Really, there is two parts to this. So the first part is what's happening within science and the original study that is creating incorrect results. So what are the forces or the factors that are leading to false positives or claiming significant results when it's not actually the case? And the second part is looking at why replication studies aren't routinely happening. If replication is meant to be the cornerstone of science, there shouldn't be this crisis. There should be regular replications being done, and naturally, there will be results that can't be replicated. But these issues should be weeded out quickly, very quickly after the original study, not having it cited thousands of times, going on for years or decades before it is then tested. So I'll look at why replication studies aren't happening regularly. So let's start with the first part, which is what's going on in the original studies that are causing results to be reported that can't be replicated, or what's happening within the culture of science that is creating this. And I think the best way to explain this is misaligned incentives. If we take a utopian view of the world, science is about uncovering the truth, whatever it may be. It's simply about increasing our understanding of the world. Unfortunately, this isn't how science works in reality. Science is done by humans, and as humans, we come with our biases. We have time constraints. We have to worry about how the results of this study are going to affect the potential funding of our next study. We have to keep those who funded the study happening, which can impact on the results. All of these real-world incentives mean that one result from a study may be much more enticing than another result. Noah Smith, an assistant professor of finance at Stony Brook University, wrote a great article about this, and I'm going to paraphrase him. So to quote, "The US university system rewards professors who have prestigious research in the past. This is what gets you tenure. This is what gets you a high salary. This is what gets you the ability to choose what city you want to work in. That's the incentive not just for the top of the distribution, but for every top 200 school throughout the nation." He goes on, "But there's no guarantee that the supply of interesting results is infinite. This means the standards for publishable results must fail, or America will be unable to provide research professors to teach all of its undergraduates. Almost every undergraduate student and assistant professor I talk to complains about the amount of bullshit that gets published and popularized within their field. Because volume is rewarded, we have tens of thousands of academics throughout the nation all trying to publish. Still quoting Smith, "Corporate sponsorship of research can obviously bias results, and competition for increasingly scarce grant money gives scientists every incentive to oversell the results to granting agencies. Popularization of research in the media, including overstatements of results, probably helps a lot with that." And that's the end of the quote. So basically, people's careers become dependent on doing research that happens to get picked up by a prestigious journal that leads to them moving up the science hierarchy. And if this is the case, and you've just spent many months or years working on a project, you're going to want to discover some significant finding within that research. And this isn't just about individuals, it's about institutions as well. They want the exposure of prestigious research. And so it's just one big machine that is forcing things in this direction. And this is because of the changes that have been happening in science and in the corporate world for decades. So for example, the philosopher and historian of science, Jerome Rivets, predicted this back in the early 1970s. So in his book, Scientific Knowledge and Its Social Problems, he said that because science was moving away from little science made of restricted community of scientists to big science done en masse with real-world incentives, it would suffer from quality control issues. So in 1970, he was touching on the same things that Smith is talking about today, that rewarding scientists for research might become dysfunctional, that the current publish or perish challenge would lead to publishing any findings, however dubious. Now, I want to be even-handed with this. The vast majority of scientists are working on projects simply, or aren't working on projects simply to progress their career. They aren't intentionally fudging results so they can get ahead. I really do want to make this clear. This podcast isn't about having a go at scientists or researchers. But as humans, we have biases and we suffer from cognitive dissonance and are able to come up with reasons for why we think interpreting something in a specific way or following some practice is best. We feel we are objective when we're often not. And when the incentives are aligned in a certain way, it changes how we view the world and view the research someone is working on. There's a quote by Upton Sinclair, the famous writer, that states, "It is difficult to get a man to understand something when his salary depends on him not understanding it." When financial incentives are involved, it makes science even more difficult. And this is especially the case if you are a pharmaceutical company trying to develop a drug that you can then bring to market. The research that you are doing is going to determine if that drug gets approval. It's also going to determine if doctors are going to start to recommend this to their patients. So Ben Goldacre is a medical doctor, an academic, and an award-winning writer. He's written books, Bad Science and Bad Pharma. Let me just share you a quote from Bad Pharma, which touches on this issue. "Drugs are tested by the people who manufacture them in poorly designed trials on hopelessly small numbers of weird, unrepresentative patients and analysed using techniques which are flawed by design in such a way that they exaggerate the benefits of treatment. Unsurprisingly, these trials tend to produce results that favour the manufacturer. When trials show up results that companies don't like, they're perfectly entitled to hide them from doctors and patients, so we only ever see a distorted picture of any drug's true effect. Regulators see most of the trial data, but only from early on in the drug's life, and even then they don't give that data to doctors or patients or even other parts of the government. This distorted evidence is then communicated and applied in a distorted fashion. In their 40 years of practice after leaving medical school, doctors hear about what works through an ad hoc oral tradition from sales reps, colleagues, or journals. But these colleagues can be in the pay of drug companies, often undisclosed, and the journals are too. And so are the patient groups. And finally, academic papers, which everyone thinks of as objective, are often covertly planned and written by people who work directly for the companies without disclosure." End quote. So if you want to read what this looks like in real life, there is a fantastic article called America's Most Admired Lawbreaker by Stephen Brill. And calling it an article is really underselling and downplaying it. It's a whole book that you can read online that goes into extraordinary detail. And it tells the story of how pharmaceutical giant Johnson & Johnson created a powerful antipsychotic drug called risperidone. They marketed it to children and the elderly while allegedly withholding data about its terrible side effects. And Johnson & Johnson have had multiple lawsuits because of this and have agreed to pay more than $2 billion in penalties and settlements. But since it was approved for sale in the early 90s, it sold a reported $30 billion worth of drugs worldwide. Now, I want to stress that I'm not against drugs or medication or pharmaceutical companies. They are creating life-saving and life-enhancing solutions, and society on the whole is better because of it. But the way things are set up and the amount of money that is involved, it makes it more likely that science starts to become construed in a way that is less about the truth and more about the bottom dollar. So let me move away from pharmaceutical companies and come back to talking about specific ways in which research can be less than ideal. And these are known as questionable research practices. Now, these is going to be like a long list of things that fall under this banner, ranging from the banal through to outright fraud. And what I'm going to do is briefly touch on each of the questionable practices, or many of them, and some of these are going to come up again when I go through some of the solutions that are proposed, because the solutions are often aimed at countering each of these questionable practices. And for each of these examples, I'm going to use people to illustrate my point. So people in studies to illustrate my point. But obviously there is lots of different types of research, many that don't involve people. So this is just to explain the different questionable practice. And I'm going to keep it very basic. And I know that research is nowhere near as simple and as straightforward as I'm making out in these examples. This is just to make it easy for people to understand. And the other part I want to add with Many of these questionable research practices, there will be times where they are completely justifiable, where there is nothing untoward, but because of the context or something specific, then it is completely okay to do this. So this is a gray area. So the first issue is selective reporting or partial reporting. So in this case, you collect all the data that you need for your study. And when you include everything, and you crunch the numbers, nothing significant is found. But if you only use some of the data, you're able to find a significant result. So for example, you have 200 people in a study, but if you look at just this 120 collection of people, that's when you show something significant. Or it could be to do with study conditions. So to start out, the study had 5 study conditions, but when you include all of these conditions, nothing significant is found. But if you leave out one of the conditions and just use 4 of them, then you're able to find something significant. So you're making retrospective changes so that the study shows something significant. The next questionable practice is optional stopping. So you take in 200 people for your study, and then you run the data and you discover it's not statistically significant. You then take in another 50 people. You then check the numbers, again, not statistically significant. You then take in another 50 people. You check the data again, and now it's statistically significant. So you decide to stop taking in any more people. So you're choosing to stop at the perfect time to give you statistical significance. In the same vein as this, say at the beginning of the study, you decide you're going to take on 2,000 people. After you've taken on the first 500, you run the numbers and see that it's already statistically significant. So instead of collecting the data for the remaining 1,500 people, you now stop and you just use the 500 people and you make it a smaller study. Another questionable practice is p-value rounding. So the p-value in statistics stands for probability value. And what it is looking at is what are the chances that the results are happening because of random chance versus the results are happening because there's a connection between some variables. And the p-value is a number between 0 and 1, with the higher it is, making it more likely that it is random chance, and the lower it is, making it more likely that it's not random chance. So for a study to show significance, you want a p-value as low as possible. And what's been agreed in science at this point, although there is lots of disagreement and argument about it, and this is something I'm going to talk about later, is that once the p-value hits 0.05, then you can claim statistical significance. So anything above that, no significance, anything below 0.05, and you can say there is significance, with the lower it is, showing stronger evidence. So the issue with p-value rounding is that say your p-value is actually 0.054. So this would actually be above the cutoff, so you couldn't claim significance. But if you cut it down to just 2 decimal places and you round it, now it becomes 0.05. And if it's presented this way, you can claim the study has significance even though it doesn't. Another questionable research practice that also involves the p-value is called p-value fishing or data dredging or p-hacking. And this was what first brought attention to Brian Wansink, who I mentioned at the start. His blog post explained that this is what he'd asked someone to do, but he was framing it as if it was a good thing, as if someone was this skilled researcher because they were able to find a connection. So when looking at the p-value, you are testing a hypothesis. For example, you have a group of 1,000 men and you want to see if their vegetable intake has an impact on their cholesterol levels. And I'm completely making this up, but let's say you run this and it turns out that there's no significance. When you did the study, you collected lots of data on the men. And so you start to break this down and see what happens when you do. What happens when you only include the men who are between 25 and 30? What happens if you only include broccoli and asparagus but none of the other vegetables? What if you only include men who are below a BMI of 25? And you just keep testing more and more segments until finally something turns up that is significant. And so the study ends up being not about 1,000 men and vegetable intake, but about some subset of those men and some subset of variables. Now, this isn't to say that this isn't true, and it could be worth doing further work on, but the more variables you start to check, the more likely is that you'll find something that says that was their significance from a p-values perspective, but it's much more likely to just be chance. Another questionable research practice is known as the file drawer effect. And this is less about replication issues and more about how it affects our understanding of the body of evidence. So let me still mention it. So let's say you do a study that looks at exercise and lifespan. Again, I'm completely making this up, but the study involves 500 women and was looking at exercise and diabetes. So you do the study and it shows no significance, meaning that exercise levels has no connection with diabetes. Instead of publishing this study, you just leave it. The study never gets published because it showed nothing significant and it just sits in a metaphorical file drawer. Now, the issue here is that then skews our understanding of the world. Imagine someone decides that they want to go and look at all the studies relating to exercise and diabetes. They find that there's 15 studies with 12 showing that exercise improves diabetes and 3 shows no effect. By looking at those 15 studies, you'd think the body of evidence is clear that exercise is really beneficial. But actually, there could be 50 other studies that are still sitting in a metaphorical file drawer, which actually showed no effect. So this would then mean that there are 15 studies or 12 studies that showed a positive effect, and then 53 that showed no effect at all. And this is a very different picture. And this actually relates to the previous issue with p-fishing, which is if the original study was done as it was intended, it would show no significance. But because the data was mined, the study now focuses on some subset to show something significant, and we miss out on the study that has showed or would have showed no effect. So the file drawer effect is a real issue, but if journals are much more likely to publish work that shows significance and scientists' tenure and career path is dictated by publishing in prestigious journals and publishing original work and publishing work that shows significance, it makes it much easier for someone to just move on to the next project rather than spending the extra time to try and find a journal that will publish something that is not significant. So another questionable research practice relates to the manipulation of outliers. So in statistics, an outlier is an observation point that is distant from others. So let's say you have 100 women in a study and you are looking at their height. Again, I'm just completely making this up. Of those 100 women, 80 of them are between 5'2" and 5'6". So the bulk of the women are in this range. Now you have women that fall out of this range, some by a little and some by a lot. So let's say by chance you had a handful of women from a basketball team who made it into your study. So you have 5 women in here who are between 6'1" and 6'3". Choosing whether to include or not include these women in the study can dramatically affect the results. There are different methods for determining what the cutoff is for an outlier, but there's no mathematical or rigid mathematical definition of what constitutes an outlier. So determining whether or not an observation is an outlier is ultimately a subjective exercise. And so you can start to test for significance when you leave them in the study, or you cut them out, or you leave some of them in, or you decide that it's fine to leave in all those tall basketball players, but you then make any woman who is below 4'10" an outlier. So it's starting to use outliers not because you think it's necessarily appropriate or the right decision, but looking at, okay, what gives you statistical significance and what doesn't. Another questionable research practice is making claims that results are unaffected by a certain variable when you are unsure if this is true, or worse still, if you know that it is. So, for example, we have a study of 500 children looking at food intake and BMI, and they find that there is some connection between what they're eating and what their BMI is. Now, as part of this, there could be lots of other explanations for why this is happening. It could be what they're eating, but it could also be the day, the month of the year that they were born. It could be linked to the total earnings of the household. It could be that the school they go to. It could be related to how many other siblings they have. There's lots of different potential variables that it could also be related to. And with research, they'll often try and rule out these other variables. So they say even when controlling for month of birth, household earnings, the school they attend, how many siblings they have, there is still a connection between food intake and BMI. So the questionable practice is when these things haven't actually been taken into account. So they didn't rule out household earnings, they just say they did. Or worse still, they did actually look at household earnings. And that's the thing that is making the biggest impact, not the food intake. But still, it's claimed that it's to do with the food and that they controlled for earnings. Another questionable research practice is post hoc storytelling. So using the data to tell a story when we don't know if that story is necessarily true. So for example, let's say you have an evolutionary biologist. They do some research and they realize that humans and chimpanzees share some trait in common. And this is some new discovery that we didn't know about before the research. Based on this discovery, a story is then created for why this might be the case. But it isn't presented as a story, but explained to be what the research has shown. Now, in some cases, there is no proof for the post hoc storytelling. It's simply a theory. In other cases, if they actually went through the data correctly, they could ascertain whether this was true or not. But this then doesn't happen. They simply make out that this has happened. And this is known as framing exploratory analysis as confirmatory analysis. So basically presenting your theory as if it is the result. Another questionable research practice is when there is insufficient oversight or mentoring. So with a lot of research, you have people with varying degrees of expertise working on it. You have someone who is supposedly running the research with lots of experience, but then you have others who are helping out who will be students in various stages of their studying. And unfortunately, those who are meant to be in charge or who are meant to be providing a mentoring role are often stretched for time. And so they're doing a lot less as part of the research than they should be. And the ones who are really running it aren't so experienced. So they put it together as best they can, but there are errors that get made. And when it comes to the oversight and the checking stage, these errors get missed. So research finds something significant and makes its way out into the world for all of us to believe. But if better oversight and training and mentoring had been taking place, this would have been avoided. Another questionable research practice is concealing conflicts of interest. So with research, there's always a section where someone can disclose this. So for example, if you were doing a study on the health benefits of meat and eating meat, and you then receive donations each year from the British Meat Processors Association, this should be disclosed. If you're doing a study on the health implications of obesity, and you are receiving money from GlaxoSmithKline, who have a line of obesity drugs, then this needs to be disclosed. This doesn't mean that you can't do research if you have certain ties to companies or lobby groups. You definitely can. But if this is the case, it should be disclosed so that when someone looks at the research, they have a higher level of scrutiny. The next questionable research practice would be overselling the results. And this could happen either in the actual research paper or in the media. So in the paper, in the conclusion or the abstract, it makes out that there's been some big result. But you then go through the numbers and what was actually found is much less significant or much less powerful. Or the paper comes out and it gets picked up in the media. And now when asked about the paper and what you explain is it's stretched or it's embellished or you create this neat, simple story which works well for TV or the newspaper, but isn't exactly what the paper showed. The final questionable research practice isn't so much questionable as outright fraud, which is someone intentionally falsifying results. And this could be anything from collecting the data and then changing the results through to completely making up a data set. So Dietrich Stapel is the perfect example of this. He's the former professor of social psychology at Tilburg University. And in 2011, Tilburg University received reports from whistleblowers saying that Stapel's research needed to be investigated. And when they did, everything just fell apart. So early in Stable's career, going back to the point of actually getting his PhD, they found that he had manipulated data. So he'd delete things, he'd change things, he'd make amendments to show significant results. But as time went on, he became just even more audacious and simply made everything up. So he developed a complete experiment at the level of theory, hypothesis, methods, stimuli, questionnaire, even participant rewards, and then would pretend to run the experiment. And instead of doing that, he would simply make up the numbers and then send those to colleagues for further analysis. And there's a fantastic article in the New York Times about Stable that goes through the whole story. And Stable talks about the allegations and when they first came up. And he had this meeting about what was going on. And at the end of the meeting, the person said, I'm not really happy. I don't think what's been going on here is right. There's going to be further investigation. And after that meeting, he got on a train and went out to a different university, a university that he'd claimed he'd done research at for many of his papers. And he needed to go there because he needed to visually know what the buildings looked like because he'd never been there before. And the problem was the research was meant to have been done years earlier, and he wasn't completely sure which buildings were around at the time that research was meant to have been done. Another piece of the research he made up looked at how closely people sit next to someone of their own ethnicity versus someone of another ethnicity. And this research was supposedly done at a railway station, again, a railway station that Stable had never been to. So Stable had to get a train there and find the row of chairs that he could say were the ones that he used in the experiment, despite making the whole thing up. So Stable eventually admitted to what he has done, and he is definitely the extreme end of things when it comes to falsifying data, given the extent that he went to. And this kind of thing is the tiniest fraction of why the replication crisis is happening. Most of it is due to the other questionable research practices that I mentioned. So those are some of the reasons why the research can't be replicated. And I now want to look at why replication studies aren't attempted very often. It's meant to be so important, so why are they being skipped over? And the general answer to this is the same general answer to why questionable research practices take place in the first place. There aren't incentives to do replication studies. They aren't going to get someone the positive exposure that's important for their career, or the university or lab doing the work isn't going to get the credit for some new discovery. And because this is so valuable for the individual or the organization, replication studies take a backseat. So let me go through some of the specifics around this. Brian Earp and Jim Everett have listed 5 points as to why replication attempts are uncommon. So number one, independent direct replications of other findings can be time-consuming for the replicating researcher. It's incredibly difficult to do a replication of someone else's work because you need to know the exact details of how they did it. While some of this will be included in the paper in the methods section, this is generally not enough to create an identical study. So you have to get in contact with the original author to find out. They might have done the study 10 years or 15 years ago. They can't remember every detail. So they say, get in contact with the undergraduate who assisted on the paper. You then do that. And then they try and find the original data so they know what reagent that they used or some other specific thing that is going to be important for how you actually replicate the study. So it can be incredibly time consuming to try and do this, and you can't always get all the information. The second point is replications are likely to take energy or resources directly away from other projects that reflect one's own original thinking. As I've already said, original research is so much more highly valued than replication studies. And so when individuals or labs are looking at what study to do, original work is going to be given precedent. And I also want to highlight the resources or the cost side of this as well. Someone is always paying for the research and they want to get something back for this money. And it can feel like it's better use of money to do original work than a replication study. And let me give some context to these first two objections to do replications, that they're time consuming and they take away resources that could be put into original research. So I mentioned earlier about the reproducibility project done by the Center for Open Science and Brian Nosek. and that was looking at 100 papers in the area of psychology. Well, in 2013, the Laura and John Arnold Foundation donated money to do a reproducibility project for cancer biology. So cancer is an area that has had trillions of dollars spent on it without a huge amount to show for it. So the project would look at 50 highly influential papers that were published between 2010 and 2012, and they would work with a team with connection with the original researchers to reconstruct those experiments, to replicate those experiments. And there's a fantastic article about this in Slate that goes through this. And like everything else I've referenced so far, it's available in the show notes. And while the replication or the reproducibility project for psychology went together fairly straightforward, this hasn't been the case with the one for cancer biology. So they discovered that to do all the studies was just going to be way too expensive. So they dropped down from 50 to looking at 35 or 37. There was a huge amount of legal red tape and legal issues. So the majority of people who were doing this research they were wanting to look into were pharmaceutical companies. So there could be years of back and forth emails just to get to the stage of signing a contract to begin the work. Then there was the issue that the head of labs were unsure of how the original studies were carried out. So a graduate student or a postdoc did most of the work, and then they'd move to another institution. So like I described before, they'd have to try and get in contact with these people and try and find out all the different details about the study. But they just really struggled to remember the finer details. They couldn't remember the exact reagent they used, or the exact strain of rat, or the age or sex of the rat at the time of the experiment. And even when all the information was available, it still wasn't possible. So, for example, one experiment called for the creation of a quadruple transgenic mouse. So this is one in which its genome has been modified in 4 specific ways. And it would have taken literally years and years to produce these mice, so they decided against doing this study. So to quote the Slate article, the crisis of reproducibility has a double meaning. In one sense, it's a problem of results. Can a given finding be repeated in another lab? Does the finding tell us something true about the world? In another sense, though, it's a problem of methodology. Can a given experiment even be repeated in another lab, whatever the results might be? If there's no way to reproduce experiments, there's no way to know if we can reproduce results. End of quote. The reason I'm highlighting this is to show that there isn't an easy solution to fix in all areas. People can agree that replication is needed, but it can be a monumental effort of time and money to make this happen. So the third reason suggested by Earp and Everett for why replication attempts are uncommon is replications are generally harder to publish, in large part because they are viewed as being unoriginal. So publishing in academia can be thought of like getting a book deal back before people would self-publish an ebook. The journals that publish the articles are like publishing houses. They want to find the next J.K. Rowling or John Grisham, and articles that are original and are going to be cited many times. That's the kind of thing they're after. So if you do a replication study, it becomes much more difficult to get it into a journal. And this is regardless of what it shows. If it shows the same result as the first study, i.e. it is reproducible, then this isn't big news. If it shows something different, i.e. it can't be reproduced, this also isn't enticing. Journals can be reluctant to publish negative findings, and in fact there's a study in Nature that looked at this issue, and they found that several respondents who had published a failed replication said that when getting it published, editors and reviewers demanded that they downplay the comparisons with the original study. The final 2 reasons why replications are uncommon connect with things I've already said. So the first is, even if replications are published, they are likely to be seen as bricklaying exercises rather than as a major contribution to the field. And the second is, replications bring less recognition and reward, and even basic career security to the authors. So in layman's terms, replication does not bring the same kudos as original work. So hopefully this explains why replication studies haven't been happening. And something I want to mention that connects to all this is the advice that I often see being given. It's advice that you do your own research, don't outsource your health, you take responsibility. Now, on the surface, this seems like empowering advice, telling people that they can do it themselves, that the power is in their hands. That's really nice. But in reality, it's largely a fantasy. Truly understanding research is a skill that very few people possess. And I put myself in the group of the masses in that it's not a skill I have. Yes, I can read a full article, but I don't have the ability to spot anything but the biggest red flags. When the author talks about the different methods they use for crunching the numbers, I have no idea if they have made the right choice of regression technique for that data, or if using one way of identifying outliers is appropriate for the study, or they should have used another one. I even find it hard to explain why I'm not good at understanding research because I don't know what I don't know. So while I can read studies and understand what the results mean at a surface level, I can't understand the finer details about why there may be issues with those numbers. And the reality is that most people can't do this. Yes, it's a learnable skill, but it's not something you can easily pick up. It's why the people that do this stuff typically spend years and years at university studying it. So we have to outsource this stuff to people who know more. Now, it's important to know who you're outsourcing this to. And for me, I have a wide variety of sources, and that's where some of those are individuals, so people that I really respect, whose opinions I value, who I think really know what they're talking about. But it can also be collections of people or things like a research review. So Examine.com's Research Digest. And I do this because I want to see different interpretations. I know that, say, this person comes with this bias, and then this person comes with this other bias. And I have sources living in different groups, and I weigh up different things and their take on different studies. And I use all of these people to help me better understand the research and what it's really showing, because I just don't have that skill set. And so this is why I think it's completely deluded to tell people to just do your own research. People don't have the skills or the knowledge to really do this. They do have to outsource this to other people at some level. So with that mini rant out of the way, let me move on to the implications of the replication crisis. So in simple terms, having research that we believe to be true that later can't be replicated means that we have an incorrect view of the world. We misunderstand how something happens. And this misunderstanding can have a huge impact because it's not just incorrect ideas, because these ideas come with tangible recommendations that affect what people or organizations or governments do. So I talked earlier about the reproducibility project with cancer. So cancer is obviously a big problem, and there's a lot of money being spent on trying to create new drugs. And when a new drug a drug company wants to develop a new drug, they'll often use already published findings as a starting place. So they go through the journals and the labs, and they look at what research has been done on some specific area to then use that as a starting place. And this is known as preclinical work. And there was a great paper looking at the issues with this around cancer research. So a drug company was looking at creating a new drug. They looked at 53 papers that were deemed landmark studies. So a landmark study is an important study in a particular field. It can be landmark because of its size, in terms of the people who are included, or the length of time, or it could be landmark because it finds something new or novel. So often a fresh area of inquiry or something that really hasn't been explored. And so with the drug company, it acknowledged from the outset that some of the data might not hold up because papers were deliberately selected that describe something new, such as a fresh approach to targeting cancers or alternative clinical uses for existing therapeutics. But nevertheless, when the drug company then tried to do its own replications, only 6 out of the 53, so 11%, could be confirmed. And this is really abysmal. Like, we should never expect 100%. That is a complete fantasy. But if only slightly greater than 1 in 10 studies turns out to be reproducible, this is a big problem. And especially because most people looking at those original studies have no idea that it's not reproducible. And it so makes up their models of the world. So I've talked about the issue of missing out on producing drugs that could save lives because of poor research. Well, the opposite can be true at the other end of the spectrum, which is it can mean that people are recommended a treatment that is actually ineffective. They eat in a certain way, or they take a supplement, or they take a medication that supposedly has scientific backing, but it doesn't help their problem. Or worse, it can cause other problems because of side effects. Now, some of this can be fairly innocent. So the researchers thought that they were presenting a legitimate bit of research that was going to help people, and it's only later than it turns out that this therapy is discovered to be ineffective. But in other scenarios, it seems more dubious, and it seems like there's more conflicts of interest. And as part of doing the research for this episode, I came across the concept of disease mongering. So mongering means selling or peddling, so it's selling of disease. And what this is as a concept is the idea that many diseases that we are being warned about aren't actually diseases as such, but rather routine parts of being human beings. So it's normal to have times of feeling sad or feeling bored or having trouble focusing. This doesn't mean that you have depression, or it doesn't mean that you have ADD. It's normal to have bones that thin as you get older. It's normal to get some gas or some bloating when you eat a meal. It doesn't necessarily mean you have IBS. And this isn't to say that depression or ADD or osteoporosis or IBS aren't diseases, but these labels should be reserved for specific circumstances. But instead, they have been much more broadened out to capture many more people who are just experiencing very normal parts of being a human being. Or risk factors like high cholesterol or high blood pressure come to be thought about as diseases within themselves. And with thresholds for both of these continuing to fall, more and more people are then considered to be sick. And this is a tricky one, because on the one hand, prevention is much better than trying to reverse something when it is set in. So having early signs or early warning signs is important. But on the other hand, if we are framing perfectly normal numbers as being a problem and then putting someone on medication or labeling them as ill, this is an issue. And so how this fits into the replication crisis is the questionable research practices that can happen to create research to show why something otherwise innocuous is now a problem. So this could be conflicts of interest that aren't disclosed, so a new disease is created, or the cutoff point for labeling someone as having disease is changed, making it more likely, or it could be other questionable research practices that prove why or tell us why we should be moving some numbers down. So what are some of the suggested solutions for all this? I've already talked about some of the limitations that we can be up against with the enormous expense that can be involved to do a replication. So some of these solutions are going to be aimed at encouraging replications, but many of them are about doing things better the first time round. And this obviously doesn't stop the need for replication studies, but it should change the percentage of them that aren't actually able to replicate. And something I want to mention is that replication studies aren't all upside. Just like original studies, they can be biased or follow questionable research practices. And for example, you could have a replicator who doesn't believe the original findings and intends to show that a reported effect does not exist. And this could cause obvious tension between them and the original study authors. It can also create bias on the part of the replicators who set up a study in the way that makes it more likely not to replicate. And there are many people in science who have had fallings out or don't like each other. So this isn't quite as outlandish as it might sound. And having a failed replication can be incredibly damaging for a scientist's reputation. And while it's actually normal to have some percentage of replications fail, even when the best of practices are followed, this kind of charitable interpretation doesn't necessarily happen. Even just rumors of a failed replication can cause immediate reputational damage by raising suspicion of negligence or questionable research practices, if not worse, where people are suspected of outright fraud. So this is something that does need to be handled carefully, because if replication studies aren't done to the highest quality, the reason the replication fails could be errors in the replication study and that the original research was correct. So the first suggested solution for tackling the replication crisis is pre-registration of studies. So before you start a study, you register a report. You describe the study methods, how you're going to analyze it prior to any data collection. And this report is then peer-reviewed, and at this stage, publication is granted as long as the authors follow the study as outlined in the registration. So this would be helpful in many ways. It would mean that the authors know a study is going to get published irrespective of the findings. Sure, there will still be a desire to show something significant because of kudos of some original discovery, but at least they know they aren't going to struggle to have the study published. This will also help to tackle the issue of publication bias or the file drawer effect. So rather than having only studies that have shown something significant see the light of day, there'll be the whole spread regardless of the outcome. It will also help to tackle the issue of partial data reporting or optional stopping or p-value phishing, because they will have to follow what was outlined before the study began, making it much harder to change things so you get a significant result. It will also help with study design, as flaws or weaknesses can be picked up prior to the research starting, and this being fed back by the peer review team. The second suggestion is sharing the study data in online repositories. So all of the data that you collect for the study is then held in a database that other people can go back and look through. This means someone can read the actual study, but they can also investigate the raw data themselves to see how it stacks up. And this is often how people are able to discover that there's something a little fishy with a study, even without doing a replication study. They look at the complete data set and they start to notice anomalies or that it has been dealt with in a certain way to create a specific outcome. One potential problem with this is if sharing this data is just optional, like it is currently. So there are already places to put raw data connected to a study, and then the study has a badge on it indicating that this is the case. So you could have a situation where the best researchers who are following the best practices are putting their data online because they feel confident that they are doing solid work. But in this climate where people are hunting for errors and trying to show why a piece of research is wrong, they are the easiest targets because everything there is available. As I said a couple of minutes ago, even just the rumor of a replication failure or questionable research practices can be damaging to a career. So it could be the people who are trying to do the best work and share the raw data then are leaving themselves most open for attack. So these first two suggestions are going to have the most impact when this becomes a requirement for research rather than something that is just encouraged. The next suggestion is emphasizing replication attempts in teaching. So students learn about doing studies not just through original work, but by doing replication studies themselves. And you could even make it a requirement that graduate students have to publish a high-quality replication attempt related to their doctoral research prior to graduation. And this would change how scientists feel about replication. It would bring through a new generation of students in which replication would become more important than it currently is. It also have the knock-on effect of making original work better because there's a much higher likelihood that a replication study is going to be done on your original work because of all these students who are doing these studies. The next suggestion then ties into this one, which is more funding for replication studies. So rather than having replication studies be an anomaly that's hard to get grant money for, this becomes easier. And if you combine this with students who've had replication studies be a much bigger part of their schooling, it could change how scientists think about these studies. They won't be having constant worry about needing original work for career progression because there'll be funding for both original work and replication studies. And at least at this stage, it feels like this kind of funding would probably be coming from philanthropic donations, wealthy individuals who believe in science and want to help make science more like the idealistic view that we have rather than how it really is. And connected to these last couple of suggestions is rewarding quality, not quantity, and judging academics on quality, reproducibility, and sharing of data. So as I mentioned earlier, there is a culture of publish or perish. There's pressure to constantly be putting out new work. But if we could shift, particularly for career progression, where there's more value placed on quality work rather than the amount of work, this would make a big difference. Especially if as part of this idea of quality, it included researchers being open and sharing their data and being open to having their work replicated. And again, this is going to come back to incentives. You get more of what you incentivize. And if there can be a shift to incentivize quality over quantity, this is what will start to happen. The next two suggestions relate to the p-value. So the first of these is reducing the p-value required for claiming significance of new results. So as I mentioned earlier on, to claim significance, you need a p-value of 0.05 or less. And a lot of people think that a p-value of 0.05 mean that there's a 95% chance that your hypothesis, the thing you're testing, is true. But this isn't actually the case. John Ioannidis, who I referenced earlier, has talked a lot about this in his articles. So his articles, Why Most Published Research Findings Are False, goes through this in great length. There's also a very accessible piece that appeared in the New Food Economy that goes through this as well. So despite feeling like 0.05 is a good way of proving significance, depending on how the study is set up and the area that is being studied, it could be proving little better than chance. So what has been proposed is that the p-value should be changed from 0.05 to 0.005. And this step would make it much more difficult to prove significance, but when it does, would create much more confidence that the results aren't just chance. And this would also improve reproducibility of scientific research because the original bar was set so much higher. And connected to this idea, which is the second suggestion related to the p-value, is addressing the misinterpretation of the p-value. As I've already mentioned, many people have a misunderstanding of what it actually means. So one suggestion for this is to use another method for showing significance other than the p-value. And another suggestion is including not just the p-value, but also including the false positive risk. So the likelihood that there's no connection and it's simply chance, but also the likelihood that what you're finding is a false positive. Robert Matthews from the Aston University in Birmingham has been one of the people most vocal about this and has been proposing changes to the p-value. And I'm going to quote him. He said, "The plain fact is that 70 years ago, Ronald Fisher, who popularized the use of the p-value, gave scientists a mathematical machine for turning baloney into breakthroughs and flukes into funding. It's time to pull the plug." The next suggestion is encouraging the use of larger sample sizes when doing replication studies. So rather than just copying the study exactly, using the exact same amount of people, the sample size in the replication study should be larger. And by having larger amounts of people, if the study can be replicated, it will then further increase the confidence of that result. The next suggestion is for people to do studies that are useful regardless of their outcome. So if a study is done where one outcome means that it has been really helpful, but another outcome means that the study feels like a waste of time, then bias and questionable research practices are more likely. But if a study is going to be helpful irrespective of the results, then the chances this reduces the chances of questionable research practices or bias. Now, obviously, this isn't going to be the case with all research. For example, if a drug company is doing research to try and determine the results of some new drug they've developed, then of course they're going to want to see some kind of positive result. And this kind of thinking also shouldn't discourage blue sky research. So blue sky research is research that is done where there is no immediate real world application for what's being studied, or when there isn't anything apparent. And this is also known as curiosity-driven science. And this kind of research is really important because often out of it, we get real breakthroughs. So this is how lasers were discovered and developed. It's how we discovered DNA fingerprinting. So there should be research being done that doesn't have a clear agenda, but is simply about exploring new ideas. But outside of these exceptions, there should be a preference given or a push made for research that being done that is useful, irrespective of the outcomes. Another suggestion, which is actually more specific for certain types of research, is to consider the litter effect. So the litter effect is the tendency for litter mates to respond more alike than animals from different litters. So for example, let's say you're trying to test a new drug on a pregnant mice to see if it leads to any birth defects in their offspring. If all the mothers come from the same litter, their response is likely to be similar. But if you test the drug on the same strain of mouse, but have them coming from many different litters, you'll see if there's a broader set of responses. The next suggestion is to use clinically relevant concentrations when doing the research. So if you are testing how a particular compound affects a human or the side effects of a drug, you need to be using it in a relevant dose. And what can often happen with drug testing is that a new experimental drug is tested against the current leading drug in the field. So the current leading drug in the field becomes the control. But while the experimental drug is given in a dose that is correct, the control drug is given in a much higher dose than would normally be used, or at the very high end of normal. And what this does is it increases the likelihood of the control having many more side effects. And then this new experimental drug appears safer because of that. Or when testing the damage of a certain substance, the dose used in the experiment is at a much lower dose than what humans would actually be exposed to. So at this lower amount, there's no side effects or very limited side effects, and so the substance can be classified as safe. But actually, if the research looked at how what happens when the correct dosage is used, we'd have a very different conclusion. And then the final suggestion is to emphasize triangulation, not just replication. So triangulation is looking at the same problem, but doing it from a number of different angles. And this is often about understanding if two things are simply correlated or if there is a cause and effect relationship. And this can be the issue with reproduction studies or replication studies, is that even if they reproduce, this doesn't mean that our hypothesis for why this is the case is actually true. So, for example, there have been many studies done looking at alcohol consumption and longevity. And what would always happen would be the results would create a J-curve, meaning that those who drank a little bit of alcohol would live longer than those who were abstainers. And then those who drank a little alcohol and were abstainers would live longer than those who were heavy drinkers. And then the more someone drank, the shorter their life would be. And obviously, I'm talking here about the averages in the study, not what occurs with every individual. But what these studies would do is give the impression that there were some health-giving properties to consuming a moderate amount of alcohol, because those who drank nothing were worse than those who drank a little. And this is what would happen study after study. So you could get the study to replicate. But what they then discovered was that the question around whether you drink or not, or how much you drink, was only focusing on now, not what was happening in the past. So if you were someone who had been a 30-year heavy drinker, you've now stopped because you've joined AA and you're dealing with liver cirrhosis, if you answered the questionnaire, you would have been marked down as a non-drinker. So when they did further research and they controlled for this, the results changed. Being a non-drinker now trumped being a moderate drinker in terms of lifespan. So there wasn't some benefit that alcohol was bestowing. It was simply that the non-drinker category had been muddied to include previous drinkers who had now stopped. So this is the idea around triangulation, rather than just simple replication. It's looking at what might be missing from the original study, or what we have to change so that we can determine if something is truly a cause rather than just being correlated with the outcome. So that is the end of this week's podcast. I hope I've done a good job of summarizing what the replication crisis is, why it's happening, and what are ways that it can be improved. And I hope I've done this in a way that's interesting and not just for the science nerds. Science more and more is making its way into the media. Studies are making headlines in the paper. But these stories are often sensationalized. They're popularized because they are novel or they fly in the face of what we thought. But despite the attention, it doesn't always make them true, or what is presented in the media isn't always what the actual study showed. And when I had Pixie Turner on the show, we talked a little about this and about scientific literacy and why it's so important for lay people. And so I'm hoping that this episode has helped with that in some way. As always, I would love to hear what you think of the show. If you have any comments or criticisms, I'm open to feedback. You can do this by emailing me at info@7-health.com or leaving a comment at the show notes, which is www.7-health.com/120. And as I said a number of times, all the papers and articles that I made reference to and read as part of this creation process for this episode will be at the show notes as well. I hope to be back next month with another solo episode, probably not to this level, something more straightforward or brief. I haven't done a life update since November last year, so it's likely that that will be the episode. Thank you so much for taking the time to listen to the show. If you are reaching this point, you've been with me for quite a long time now, and I really do appreciate it. So take care, and I'll be back with a new episode shortly.
Thanks for listening to Real Health Radio. If you are interested in more details, you can find them at the 7 Health website. That's www.7-health.com.